first study that we performed with the system was actually measured several cataractous eyes or cataract suspects, and you can see how the crystalline lens, how the optical properties of the crystalline lens change compared to the healthy ones. You can see some specific opacifications, and they are not only hyperreflective opacification, but there are also some hyperreflective opacification, some hyperreflective regions, and also, for example, this is nuclear cataract, and so the OCT can map all those opacifications precisely. We can locate them in the space. We can make some specific post-processing of the data and generate some maps of opacifications from the cortex, from the nucleus, because we have access to the 3D data. We can do also some opacity characterization as well as the grading, cataract grading, and you can see that the signal, generally the signal increases with the grade of the cataract. But this was our the first study. But we also, in this study, we also used the double pass system, the OQS analyzer, which measures the optical quality of the eye by measurement of the objective scatter index. Objective scatter index is the relation of the point split function in the periphery with respect to the central part. So simply speaking, is the double pass system. And the more forward scattering in the eye, the higher objective scatter index. So this system measures actually straylight. And the other was visual acuity test and contrast sensitivity test, which was performed by Adaptive Optics Visual Simulator. It was a standard contrast sensitivity test. So we measure area under log contrast sensitivity function. And if you can see a number of the images for, these are normal subjects for a different age. So we had 50 participants from 8 to 78 with no ocular pathology, no eye surgery. We didn't use any pupil dilation, and we measured in mesopic conditions. And you can see that generally the thickness of the lens increases. And also the signal, if compared to this one, the signal generally is higher. So it means that there's more backscattering in the lens. But we can make this description more quantitative. We can compare also these images. You see that the images of the lens are not really like homogeneous. But we can compare this with the Shankook imaging and the Oxford cataract classification system that was used. And also people like Dubelman or Augustin, they noticed that you can actually define some layers or some zones, and these are called optical signal discontinuity zones in the lens. And they were used for Oxford cataract classification system. And we performed the same procedure or similar procedure to the OCT data, and we will show the results. So from 3D data, we actually get the central, central depth profile, and we were able to distinguish different layers. We also checked the curvature of the crystalline, the curvature of the anterior, posterior, and also the nucleus. And so, as far as for the thickness, you can see that with the age, the thickness of the lens increases. And also, and this is mostly affected by the growth of the cortex. The nucleus doesn't change very fast with the age. You can see here that this is a statistically significant change. But also, we can draw the conclusion. We also related the whole thickness, the thickness of each layer to the whole lens thickness, and you can see that the contribution of each layer is actually for the C3 layer, which is the bright layer, increases, and the contribution of the C4 layer decreases with the age. And there are statistically significant changes. As for radius of curvature, you can see that with the age, because the lens grows and the lens thickens, so the radius of curvature decreases with the age. and this is statistically significant. However, in this case, we had to apply some method to correct the images for light refraction, and we used double shell model. So we only distinguished cortex and the nucleus. So the posterior surfaces probably they are not so accurately measured. But what we see is that the anterior lens capture anterior nucleus and posterior nucleus. They change. The correlation with the age is statistically significant. So what we also observe is that generally more backscattering occurs in the cortex. The lens with the age becomes more opaque, and mostly is responsible. Cortex is responsible for the opacification, and these processes are not so fast if we consider the nucleus. And this is mostly C3 layer that gives the largest correlation with the age. We also checked the impact of optical quality on optical quality and vision, and we can see that the signal, the description of the lens OCT signal with respect to the OSI, so backscattering versus forward scattering, there is some correlation between those two parameters. It's not very high correlation. It's because these processes are different. These are different processes, backscattering and forward scattering. So what else we can observe is that generally the area under contrast sensitivity function the correlation is higher than for visual acuity. And there is also difference between the correlation of OSI and the signal from OSI. It's because what affects the vision is actually forward scattering, not backscattering. And I want to also show you another effect that we could observe. We noticed in the images is the lenticular sutures. As I said before, the lenticular sutures are the planes or some surfaces where the fibers meet each other. And the suture geometry increases with the age. These were these early papers of Kusha. And also, we didn't know what we observed actually. We started digging into this, and it seems that actually lenticular sutures, it's very hard to observe them. Maybe if you have sutural cataract, then you can observe them clinically in vivo, but there are some rather microscopic methods, studies or indirect methods that allow to visualize the impact of sutures on the quality of the eye. However, in our case, we perform specific analysis of our data. So we use these labs from the cortex, and this enabled us to generate the projection images. And you can see that there are some bright branches, and these are actually sutures. And we did some kind of processing in order to get the information about the structure of those sutures. What is really interesting, I'll show you the movie showing on fast flight through different depths of the lens, and you can really see that we have this complex pattern, and there's also this BMW pattern, this Y and inverted Y pattern in the nucleus. And we were able to extract this information and to segment and to generate some kind of three-dimensional structure of sutures. And this enabled us also to generate the maps of sutures in the anterior cortex, in the posterior cortex, and the fetal nucleus and posterior fetal nucleus. And unfortunately, we see that the complexity, if we go across the age, the complexity is, we don't see that we observe more branches if we increase the age. It's because our field of view was limited by the size of the pupil. We didn't use any dilation. Probably if you use dilation, maybe you can see more. However, we observe also that the signal from the sutural regions increases with the age, and it's higher than what is between. However, this is the method for in vivo visualization. I think that this was the first method that shows in vivo visualization of the lenticular sutures. So to summarize, we showed the comprehensive three-dimensional visualization of the architecture of the crystalline lens in vivo, and this was presented by showing the optical signal discontinuity zones and also lenticular sutures, we showed also opacity mapping, 3D mapping, that shows some kind of local degeneration schemes during cataract development. And we performed also quantitative description, and this is objective evaluation of the scattering. And the conclusion is also that the cortex contributes more to the lens thickness change with the age than the nucleus. And also the nucleus and cortical C2, C4 zones contribute to the increase of the opacification of the lens with age. And the most significant age-related changes take place actually in C3 zone. Also, scattering has a negative impact on vision quality, as we could expect. And so we can consider the OCT as the tool for fundamental studies on development and aging of the human lens. And also we can, by doing this study, we can have kind of like improved understanding of the structure-function relationship of the human lens. At the end, I'd like to thank my team and also collaborators, in particular Barbara Kryszczionek and Pablo Arto, who contributed to the studies. And I'd like to thank also the support. Thank you very much.
The people is open for questions. So scattering is very wavelength dependent. So the assertion, I assume you're using infrared light?
Again?
I assume you're using infrared light for your OCT?
Yes, so the system operated at 1 micron. Yes.
Yeah, so I'm having a little trouble correlating infrared light to visual significance.
Yes. So the initial idea was that the system will be operating in the visual in this region, right? But it's very hard to get actually there's no light source that we can use to make the OCT system. But actually you are right, this should be done in visual, and then it will be more clinically significant.
So yeah, I think that's.
So that was a trade-off, and we had to.
I understand the trade-off. So, but that explains a lot of the lack of correlation, should I say, to
yes,
other stuff.
Exactly.
Yeah,
so that's why this is why the correlation is not very high. Right?
Yeah.
Yes.
Thank you.
Exactly.
I just have a quick comment about the sutural maps with branching. And the fact that next one, doesn't seem to change much in the sort of 6-7 decades of life, but the lens has pretty much stopped growing. And the reason you're having the sutures is because of the way that the fibre layers are put down. So there has to be some link to the growth mode, but also to the mechanics, because when the lens accommodates, there surely has to be a change.
You mean geometry?
No, I'm talking about geometry. Mm-hmm. But there has to be a change in how these maps appear in the different accommodated states. And that, of course, will cease after 50, 60. So I think there's more to be explored there. I think it's fascinating. And thanks for quoting Kushak's work. It's seminal, it's brilliant stuff.
Mm-hmm. This is interesting comment. We didn't consider that aspect of the study. Actually, just in my opinion, is that we are able to get this beautiful projections because of the design of the system and high sensitivity of the system, which probably is not provided by commercial systems. That's what I can comment. Yes. Actually, this was, we didn't know what we were observing, and we started digging into the textbooks, and that's, wow.
Okay. That's very nice work, and reminds me a little bit of the stuff that we try to do also with the crystalline lens. My question, Mimik, is how you define this mean signal? Is this just like an average over some area?
You mean here, generally how we are segmenting the three-dimensional structure, and then we take the mean value of the signal.
Okay, but you mean the mean value of your what's in a p-scan already?
No, three-dimensional.
Oh, I see.
Three-dimensional data.
Okay.
And remember that OCT data usually are shown in the logarithmic scale. We need to, because we have access to the raw data, we have to use the linear scale in order to.
Okay, but do you use raw data for that, or?
Yes.
You use the raw data, or
yes,
you do? Okay.
Of course, this is some related because it depends really on the power that you have on the eye. So from system to system, it may change, right? But the commercial system will not provide you access to raw data, right? Simply speaking, you have just images, JPEGs.
I have a short question. Can you go to the figure of the optical density versus age? To the graph?
Yes. This one?
Yes. I can see in the y-axis that is multiplied by 10 to the 4th is the optical density.
I don't remember how we define this. This is probably just signal. We call it optical density. Maybe this is not really. I tried to find the metrics of the name. It's probably not proper name because optical density. But I noticed in the literature that people use that like more. They are more relaxed in using this. So yes, you're right.
Okay.
From physical point of view, it's not correct.
It's totally dark.
Yes.
It's totally opaque.
Yes.
Okay. Thank you. I think we can move to the next session. Next talk.
Me, I'm Jesús Armengol from the Applied Optics and Image Processing groups. Fatima, Fidel, and Maria are my co-workers in this work that is entitled Through Focus Energy Efficiency in an Astigmatic Model eye with Intraocular lenses. Well, what's the leading idea of this talk? We want to find an objective optical quality metric for focus analysis of optical systems with astigmatism. And the condition is with similar performance of that of circularly symmetric systems. What I mean? I mean that the industry of IOLs, ophthalmologists, etc., are used to work with this kind of course that said, for example, that in a multifocal IOL, at the far focus or at designated power of the lens, we have a quite quality vision, and in the near focus, in this case, we have also some quality. Here is a photo. They interpret this course in different ways. But what happens when we are dealing with toric lenses with astigmatic system? We do not have any equivalent course of these two orientings. We oriented these lenses in two different directions of the astigmatism. In this case, we have, for example, the area and the MTF in the vertical and the horizontal directions, coinciding with the astigmatic axis. And if we read these images in the same way the graphic before, we will say that we will see better in the storm foci of the lenses, in spite of the center of this confusion that is where it's supposed to, we're supposed to see better. In our group, we have several optical benches, and this is a schematic of one of them, where we can change lenses, use different tests to measure different optical quality indicators, some different corners with different spherical aberrations. We put an IOL in the physiological solution and get the aerial image with an optical system where then we can move to focus and get to focus curves as we have seen. We can measure MTF-based analysis or energy efficiency-based analysis as we will talk now. So, light in the bucket is an optical image quality that well established and measures the energy falling in the air defined by the chord of the diffraction limit PCF. When we have bigger keyholes, we used to work with energy efficiency, so it measures the energy at the core of the image, used to the energy that is spread around. Well, we can do that easily with, for example, in the case before, we have this kind of through focus video of what is happening all through focus, where we can have, okay, we can stop it. Well, we can see that there are two different points where it accounts for the first and the second peak. What happens when we have an astigmatic system? We change the IOL with a atomic IOL, and we have, the first we see we have an elliptical spot. Then we can do the same analysis, but adjusting an ellipsis of the core in spite of a circular symmetric. What we have is a core that has this kind of energy efficiency that okay. Here, here is one of the stone foci, here is the other one, and the center is the circle of this confusion where this ellipse is set. If we analyze this as a result, we will say that we have some quality optics in the stone foci, another quality, or much quality, but much quality out of the where it's more the focus group. So it's not really good or a code that we can interpret as a function of a quality. Then what is happening here, or what we are thinking that here is happening, there are two issues that must be addressed. One of them is that the area of these ellipses we are adjusting is not constant around the focus scale. When we scan a circular symmetric system, we have a spot that is circular and don't change through the focus, or don't change much, don't change only with the magnification, it's a small change during the focus, but the area is the same, basically. But when we have a astigmatic system, we have ellipses, the area of these ellipses is smaller, see, at the stone foci, the area is smaller, and the center of confusion, this confusion, the area is bigger, and it's bigger all around when we focus the system. So, our purpose is to have we have to change the energy efficiency to an energy efficiency per unit area. So if we want to have the idea of how concentrated is the energy in the core, we need to measure it by unit area. So if we debate, we make the division of the energy efficiency we've seen before by the area, we have this other curve that is nicer, but it still don't. It still says that we have better quality at the stone foci of the lens. What is the next step, or the second issue we think we have to deal, is that we have to favor circular images in front of elliptical ones. So if we say that the eye will focus on the circular images, we have to make some counterpart of all favor the circular symmetric systems. And that we can do it with some factors, for multiplying the indicator. We have changed it, we have tested some of them. Here we have 4 that are basics, that are basically two different frames. One of based on the semi-axis of the elliptical of the ellipses we are adjusting. The ellipses have two different axes, semi-axis, one big and one smaller, and if they are equal, they are circular, this factor will be 1, and if they are dissimilar, this will be less than 1. And the same for MTF-A, the area under the MTF, in the horizontal and the vertical directions. We can make some on indicator similar to that. And the same indicator we can have with an exponent in this part of the equation. Okay, when we have when we use these indicators, Okay, this is the factors have the shape, so it's one in the circle of confusion, and its minimum, all factors are quite similar form. And when we multiply it by the energy and efficiency divided by the unit area, we have this kind of curves that seem to be better indicators of optical quality. One of the conclusions we can have is that nearly, okay, that both factors accounting for the MTFA and both factors built by the semi-axis perform quite similar, so we can have it as equivalent. And the factors that have an exponent, the two upper here, the second ones, are less peaky and are more soft around the circle of the confusion than the ones that are with without exponent that have a peaky circle or less confusion. Okay, then it seems that we can have another indicator that accounts for the optical quality and read it as the previous one. We have that measured that for different powers. Okay, these other ones. So for lenses with 3 diopters of astigmatism, and here we have just the course with the factors with the exponent, with 3 diopters, 2.25, or 5 diopters, and they seem to perform in the same way. So, what's the next step for our work once we are here? Next step is we have talked about the normalized factors, and we have said that are these ones, and we said here we put 1.5. And the question is that the best exponents we can have? We have done that with the optimization, with the measures we have done, but probably we must work better to say that if this exponent is the best one or not, or we have to adapt that. And the second step is now, that is our goal now, is we are now optical model with a much more physiological cornea, and we have a deformable mirror and a loop with a Harman shaft that we can simulate a cornea with any degree of astigmatism, and then put a toric IOL in the model eye and see what is happening, and use this to focus PA's analysis with basically the MPF or the energy efficiency, and see what will happen with the interesting things now that are what happens when there's a residual astigmatism, how we will see better or worse, and what's happening with these new toric IOLs with new designs. New toric IOLs are not usually now a big convex toric IOL, but they are used as the basis multifocal IOL or EDOFs IOLs, or IOLs with working with different amount of spherical aberrations to achieve more deeper focus. So the torical version of these IOLs, how do they perform? We can analyze it and say it looks better. Okay, I think now will be time for questions. Thank you very much for your attention.
Any question? So I'm a bit puzzled because the optical transfer function depends heavily on the phase transfer function, and the focus on modulation transfer, I think, is missing a lot of the visual information that you could be obtaining by using, calculating something like the visual strail in the spatial domain and correcting for where the peak is located in energy. So I would encourage you to include a little bit more.
Okay, well, when we have, or I mean MTF-based, we have like LSF and then MTF. Yes, we can have all, this same normalization factor could be used also with MTF-based analysis. And one of the things, MTFA is one of the most usual indicators used by ophthalmologists that use IOLs, but we can also calculate visual state ratio based on MTF and OTF, etc. That's for us, for one, it is interesting, but for focus on the ophthalmology is loose.
I know, but I would encourage you that we need to do some educating about what is visually significant. I think the clinicians as a whole need to have a bit more understanding of what's actually happening visually, as opposed to focusing on the MTF that's ignoring the phase transfer function.
Yes.
I would go a little bit further and also go for like a 3D representation rather than just looking at the vertical and horizontal axis, to actually look at, let's say, this VSOTF, but calculated as a volume rather than as an area. And I understand that for that you would need to have you would need to measure aberrations, right? So I don't think with the photometer you can achieve that, right? That's your particular reason why you're using just the horizontal and vertical axis, or this is also something that it is common for ophthalmologists to sort of understand just two axes?
No, it's a practical. It's just a practical approximation, because we one of the best objects we can have is a cross section that we have small slits, and it's a practical measurement of the LTF. We have moved from circular rotational astigmatic lenses to astigmatic lenses. Maybe we can move also to make a 3D an OTF or measured in spite of 2D.
Because you could rotate that slit, for example, right?
Yes, of course, yes. We mainly consider with astigmatism.
Thanks. It's time to move to the next paper.
So I'm going to present you a new design for a new presbyopia correcting IOL that has some advantages. At least I think it has some advantages compared to current IOLs in the market. So I think everyone is familiar with presbyopia correcting IOLs. So many of those are diffractive IOLs. So most of the lenses that are made for a full vision range. This is a new name that came out now in the new ISO standards. Full visual range. It applies to lenses that have a large pure focus, that is more or less continuous. And this design that I'm going to present today, it's included in that new category. So diffractive IOLs have many advantages to be used as presbyopia correcting devices, because they are very efficient in focusing light in discrete points. So you can have bifocals, trifocals, and focal lenses with this type of structures. So they are not new. They were developed for biomedical purposes. They were developed in the late 20th century, and they've been quite improved since then. So we constantly, every year, we see a new model in the market. So now the market is full of new IOLs. Some are refractive, many of those are diffractive. The ones in this category that I mentioned, full vision range, mostly of them are refractive. So they are very efficient. They have a big advantage compared to refractive lenses, that they are very pupil independent. So it can give you the same optical quality more for a large range of pupil sizes and in different illuminations, as at nighttime, at daytime. They are quite robust in that sense. So that makes them good devices to be used like that. But they also come with some drawbacks, and that includes many side effects as night photic phenomenon like halos, starburst, and these are one of the main limitations of these lenses. So that's, I think this problem is the problem that restrains this type of devices, the market from growing more. So this is like a simulation of the type of severity that some patients might have with this type of devices. So they can be like, normally they occur at nighttime when the background is black, so that light that forms around bright light sources gets intensified by the dark background. So, and depending on the patient and depending on the IOL model, this can be mild to quite severe. So one of the issues that still needs to be improved in these devices is how can you reduce these side effects to the limits of physics. So there are, when you're talking about multifocal systems like this, you're talking about simultaneous vision systems. So there is a part of these symptoms that you cannot eliminate, because you always have a part of the light that goes through the pupil that is out of focus. So imagine if you have a bifocal lens and if you are looking at distance, you always have a part of the light that is focused here that is going to be out of focus. So that part you cannot get rid of. So it's intrinsic to this type of designs. But there are other issues. There are other issues that are related to the design of the lens in the manufacturing process that can be improved. For instance, in here you have a very nice comparison between a monofocal lens at the left and a trifocal lens from Alton at the right. This is from a very nice paper that makes this analysis, this comparison of the straight line generated by the diffractive lenses compared to a monofocal lens. And you can see that, maybe you don't see it very well in here, but you can see that around the light source you have this light veiling. So, and this obscures the field of view of the patients at night. So the larger this is, the more bothersome it will be to the patient. So the question is, how can we reduce this but still have a lens that can deliver a good through focus, that can still deliver good visual acuity at intermediate and near reading distances. So I took this lens, by the way, sorry, the Panoptics, is a lens from Alcon, is one of the flagships right now in the market of the full vision range category. So I took it as a reference to compare it against my design. So I took the face profile from this lens, from the patents from Alcon, and it looks something like this. So if you look at the lens, it has the pattern. The pattern is these three elements here. These two jumps, these two steps, and this flat step, and it repeats itself. So if you would plot it in R squared instead of R, this would be a repeating pattern of three elements. So it's actually a quadrifocal lens by design that works more or less like a trifocal by putting just a small percentage of the light in the first intermediate focus. So, and you can see if you do a Fourier transform of the period of this light, this is how the amplitude of the principal Fourier coefficients looks like. So you see that you have more or less three principal foci. But you can see that because it's a repeating pattern, it's a diffractive lens, you can see that you lose part of the energy. You don't have 100% of light in here. So you lose part of the energy to these harmonics, to these higher order harmonics. So these are focal distances, multiples of the principal focal distances, where some light goes through. And this contribute to the viewing that you were seeing before, to this light that you see around bright light sources. So they do not contribute to functional vision, but they contribute to decrease the image quality and to increase night vision symptoms. So what I try to do is, okay, so I'm going to see which design I can come up to that has the highest possible energy efficiency. So it is a very basic idea. So if I put most of the light inside the range of focus that the patient is going to use, it means that I have less light outside that range of focus that will negatively contribute to the image quality. So this is the main idea. If you put more light in here, if you are able to make a clever design that puts more light in here, then you have less light outside contributing to that viewing. So what I did is to create a design with an optimization algorithm that it's not limited by shape like the previous design here. This is a kinoform design, so it follows this parabolic shape. And this one is a freeform design. So it's like seeing what type of form, what type of shape gives me the best possible light distribution. It turns out that this design can be modeled by a sinus series. So for this one, I need to use like 27 coefficients to properly model it, but it can be analytically described with this type of formulation. And with 27 coefficients, I already have like 99.99% of the profile well described. Another advantage is that you can see that in this type of profiles, they have to be manufactured with real tool size, with tools, diamond tools. And so these steps that you see here, they have a certain curvature depending on the size of the tool. And you probably see it better in here. So this is, the tool creates this, which is a transition zone. And these transition zones that are created by manufacturing, they scatter part of the light. So they create even more viewing. So the other advantage of this profile is how to create a diffractive profile that doesn't have transition zones. That is a continuous, smooth profile with a very high diffractive efficiency. So that's the basis of this design. And the final shape that you can see is this blue curve. You can see that if you compare the normal diffractive with these steps with the new one, you see that the new one has these very smooth modulations in the shape. It's completely continuous. One drawback of this approach is to do it without steps, in order not to introduce steps and not to introduce transition zones, so you can manufacture it very smoothly. You end up with this. So normally diffractive lenses, they produce negative inverse chromatic aberration at positive diffractive orders. So, for instance, a bifocal lens, for distance order, it will only have the spherical, the chromatic aberration of the base refractive lens, but at near it will have negative chromatic aberration that kind of compensates the one from the cornea and the one from the refractive element. So it has a positive effect. And that's what you see here in the panoptics. So it's 0, and then you have negative chromatic aberration, the longitudinal aberration at the intermediate and near that compensates the positive chromatic aberration of the refractive base element and the cornea, so of the phakic eye. The drawback with this approach is that we use a negative order for distance vision in order not to introduce transition zones. So the lens has some positive chromatic aberration that will have to the positive chromatic aberration of the cornea, in the distance focus. But by doing it this way, as you can see here, this is a pentafocal lens. So you have 5 major foci. By doing it this way, you can attenuate this effect. For instance, in the market you have like a trifocal sinusoidal lens that is also continuous and it uses a -1 order for distance, but the chromatic aberration that induces at the distant foci is twice of this one. So by doing it this way, I kind of attenuate this negative effect. So and reduce a lot this drawback. So I'm going to show you some simulations of the performance of both lenses. So very quickly. So the lenses, in the simulations, only the diffractive profile is different. So all the rest is the same. So the only difference, I made all the lenses the same shape factor, the same material, only the simulations are quite precise. They use a large number of points to sample well the transition zones, and you use a lot of wavelengths, so you can recalculate the polychromatic PSF. As you can see, you end up with a very, very efficient profile that has a larger NTF, a very continuous NTF area, that you can see MTF area here, and you can see a conversion from MTF area to visual acuity using a non-linear function. This is from the Sharon papers. You can see the reference in the abstract. And you can see that the predicted visual acuity is a little better here in the intermediate zone for the new design. And for the larger pupil, it was a little bit in here, but you can see that you have a very continuous through focus with this new design. You can also see that here the peak is broader, so it seems like you also have more tolerance around to refractive errors around the main foci. You can actually see that in here, so in these Luzaf simulations. When you compare, like, if the eye is a bit myopic after surgery, it will have a better image quality with this design than with this design. So you have a little bit more tolerance to refractive errors. This is just an analysis how the lens will behave under tilt and decentration day, because they have the same shape factor, they don't differ that much, so they are similarly affected by tilt and decentration. And this is how the contrast sensitivity is affected under glare. So in here we have like an ideal observer calculated with the Barton model, and we put a glare source at 3 degrees, and we calculate how much the contrast sensitivity will be impacted by the glare. So it's calculated with these formulas that you have here. So we have here both PSFs. So we also have a monofocal for comparisons to establish the baseline, and you can see that you have much less light in here with the new model, and it's much higher with the reference model. So when you translate this to this, you see that contrast sensitivity is much affected with the reference model than with the new model under glare conditions. So we expect that under glare conditions during the night, that people with this new model will have less dysphotopsia, less halos than with the reference model. This is also some simulation to illustrate that. You can see here, you can see more viewing around the light source with the reference model, panoptic light, and with this one. And that's all I have to show you.
We have time for one quick question.
Hi, nice talk. Can you just tell us a little bit more about the surface profile of the design? Because it seems a little contradictory to call it smooth yet diffractive.
Yeah, but it's not. It's a full diffractive lens that is. I don't know if you are familiar, for instance, with the optimal replicator. This is published like in the 90s, for example. It offers a very high efficiency. It's a smooth profile. It follows a sinusoidal. So this is like a variation, but it is more complex than that, and it offers more focus in positions. But still, it's still diffractive. In the sense that you define a diffractive, also it's a repeating pattern with the discrete foci and inverse chromatic properties, etc.
Thank you.
Thank you, Miguel. We move to the next paper.
So stepping back, and I think trying to scale the far periphery led to these things up here, which I hope to speak out to see. Things that were unexpected. So the nodal point, which was mentioned today, is really for praxial values, very small angles. You know, the input angle, which was the output angle, is kind of a nodal point thing. But it turns out that when you go into the periphery of the eye, and it seemed like many people knew this before I came across it, if you draw a line that goes through the nodal point that isn't a ray, it points to the right location on the image. I mean, it just seems like in the literature these got modeled together. And I'm happy for somebody to explain that that's wrong. So my summary of it is, if you have an optical system like this, you're not hitting properly. If you have an optical system like this, you end up with both these properties. You get this praxial property with another point at small angles, and it also gets this pointing thing, at large angles. And there was kind of a German word that had direction ray. I'm not sure we have a proper phrase in English for it, because it never really came up. And something I meant to emphasize a little bit is this nodal point at f prime to n prime. So I realised when I actually get to the end of the road that I'd always done this, and I'd always noticed it. But the whole, if you look up where is the nodal point, you get the input angle equals the output angle stuff. And Zemax has always done this. You calculate the focal length and divide it by the refractive index. But they never bothered published it, or I'm not sure who came up with it. It's kind of there in the literature, but nobody really emphasized it. So, and this is still background, but I really like this picture. You know, Professor Strasberger found that this Leonardo manuscript, where Leonardo pretty much said, you can see beyond 90 degrees, but it's a bit ambiguous because it's a single eye and, you know, it's like a cyclopean vision or something. But there's no explanation as to what Leonardo was doing. But you can see that he would be interested. He would say, well, how far can we see? And he'd make a sketch, but whether he did anything to it, I don't know. But getting back to this presentation. So Dr. Cook from Michigan had a patient who came in. He's always been interested in dark shadows, because this patient came in and said, I see double images in the far periphery. On both sides, actual double images. And they weren't really bothered by it. But his office staff sent me photos, which I transcribed to these very bad representations, because of course, you know, you don't want to get into some kind of a confidentiality issue, but the picture is very clear that the patient is actually reporting the shadow out here and pointing to it. So the patient held up their fingers in both eyes. It was the same. So these are kind of stylized images. And the eye parameters are relatively normal. Normal axial length, normal corneal power, these were mid-power, Alcon, non-aspheric IOLs, if you like. And the object distance was kind of about here, so it's like a very high, a very close object. So definitely very large. But the standard testing for vision in the periphery is perimeter, only goes out to 90 degrees. And there's some papers in the literature where patients can see shadows at all kinds of distances. You know, if you put a patient with an intraocular lens in perimeter and ask them, do they see shadow-like stuff? They do, but they're not necessarily the bothersome shadows. It just seems like the negative dysphotopsia bothersome shadows are really in the far periphery. It's kind of related to this double image business. So they had anterior photographs, images, and an additional thing showed up. So the iris is thicker on one side than it is on the other, in both eyes, which actually is beneficial for seeing the double image. You know, you've got a thinner, the light that's passing the thinner side of the iris has more room to pass. And it's also decentered nasally, which is typically the case anyway, but you get even more opportunity to get that light in the periphery to pass. I put this view of eyes from below. So before I was saying this, I hadn't realized the convention, and it could be that everybody knows this. There's a convention of displaying images bestowed from below, and I suppose I have it on a separate slide now. I'll come back to it in a minute because I'll point out where it comes from. Anyway, setting this up in Zemax, so you can use the patient characteristics. And I set up two fingers, a black finger on a white background and a white finger on a black background. Zemax has no tools whatsoever to do this, and the further out you go, the point spread function really varies dramatically, just where this is on the next slide. So you can set it up. You can overlay the two things to some extent. Even just looking at the size of this is kind of a near object. This is physically what it looks like on the side of the eye with an average retinal diameter, if you like. It looks huge, doesn't it? But you definitely get these two things, and in principle can see two images. So the point spread function itself looks like this. You start out with a blob at a certain angle, and as it increases, you start getting this, you get the blob on the line, and ultimately you kind of average it out. And then eventually you end up just with a line in the far periphery as the angle increases. It's hard to explain without you doing it. So this patient is saying, I'm putting my finger here and I'm seeing a double image. But if you go to lower angles and higher angles, you can see something else. You know, and then there's kind of a dynamic component to it too that isn't captured in this. But the images themselves are simplistic modeling of it, if you like, with only approximate scaling, because it's really difficult to do. Is you start out with one finger, but you see two. On this side it's clearer. On here you also get the shadow-like component, in addition to seeing the double image. And this is the variation of pupil size. So with bothersome peripheral dark shadows, it's always with small pupil, and probably with a bright illumination, which is more this situation up here, where you can see a very distinct shadow, whether or not you see the double image. With other patients, this patient wasn't complaining. So so happened a few years ago, Dr. Maria Musica Wojciechniak had sent me some images of the iris. Because one of the related things, I was looking at this before, you know, how does the iris location impact light entering the eye? The second thing I actually mentioned is you need clear cornea as well. You need both clear cornea and the ability to bypass the iris. So I had these images and I went through them, and some of them have kind of a thicker region on one side rather than the other. And I thought maybe 10 to 15% without doing any study of it. I don't know if anybody's had a stuff like that before. I don't know if it's a family characteristic, and that's why I asked Dave, you know, does she come from a family with a particular historical background that might lead to this characteristic in both her eyes? And, hasn't been Nancy yet, but maybe when the patient comes back, they might ask. This is my thing about viewing from the feet. And everyone knows it. So it seems like the people who first set up a CT scan had to work out, do you display the images from below or from above? You know, and they decided that you're looking at the patient from the feet, just display it like that. And it seems like the anterior and maybe other things also display it from that orientation, but don't necessarily summarize it like this. So originally I was thinking the eyes were going around, but when I assembled it like this, it just seemed like this would be the way to assemble all images. Like you're looking at a patient from the feet, and so that you know which eye it is and which way it's looking. And I actually have a poster tomorrow. This reminded me of a different topic. So I've got a poster comparing the two eyes, where one eye is protruding. And there's a lot of ophthalmic instruments measures one eye at a time, but you've actually got two eyes. And if there's a difference in the protrusion, maybe at least add that to a piece of equipment. It's a very rare thing to come up. You really want your instrumentation to tell you about something that you're not even thinking about because it's so rare. So this is really the main things, you know, the visual line from negative disc. Really, the clearest thing is that it's a slit, you know, in the original literature, it's pretty much no angles, and then there's this ambiguity about perimetry measuring angles, you know. But if it really is the case that a patient can just use their fingers and point to it, and then you take a picture and analyze it later, it seems like that would be useful. And this is really the final slide. Yeah, and it just seems like it never came up, you know, before IOLs were created, and nobody's interested in the far periphery, but if you model an intraocular lens in an eye, it has to be next to the light angles. The light just doesn't get through the lens anymore. Whether or not patients see shadows because of the peripheral region. And then the thing is the iris is something that's just not monitored. And it just seems like in this day of computers that you can monitor everything and then track things and just see it as useful for telling you about something that you never thought about. And it just seems like it's related to dark shadows too, even though there isn't a definitive conclusion. So that's the thing. If you have any questions,
any question? Right. So Michael, I'm curious, I mean, it seems like what you're really saying is that periaxial optics works very well as long as for these IOLs in the far periphery, but in the real world, the pupil's quite large. Right?
No, I'm saying that the praxial nodal point is not relevant to this use of the nodal point for a very large
see.
It's like the cornea is highly curved and the retina is highly curved, and for whatever reason, if you have an optical system like that, you get a small angle effect and a large angle pointing effect. But it's not a ray effect, you know, it's hard to. We don't have a concept of a directional ray.
Gotcha. Thank you.
Michael, I was just going to ask you something a little different. Has this been noticed more in patients with blue irides compared to darker irides?
I don't know.
Because dark iris absorbs. It's worth looking at. The second point, is it noticeable more when a patient is upstanding and the patient is lying down? Has that been looked at?
The literature is just vague as to what the patients complain about and where they complain about it. So, but it's generally a very bright illumination, and my guess is it's like you go into a supermarket and you see shadows and it bothers you. You know, that like things move, you see like a double image in the periphery and it bothers you. So it's a like thing that comes and goes. But then when you ask the patient about it, they say, well, I see a shadow, and yeah, I mean, after 20 years of people describing it, nobody's really described it. you know, even for one single patient, what is it that really bothers you? You know, it just seems like there isn't that description.
In one of the last slides, you showed OCT image, and which was indicated as double OCT image. What does that mean? Previous slide, I think. Yeah, double image patient.
Okay, it's this actual patient, this one patient who sees the double images.
Oh.
I was just trying to say,
okay, thank you.
Those are the images of those patients where you've got a very pronounced, isn't it? You know, the iris is really thicker on one side. I just happen to have these other images that are generally much larger pupils, and you can kind of see it, you know. It just seems like it would be a parameter to track, wouldn't it, in case it's indicative of something else. It costs you nothing, in principle.
And what do you mean, short normal? What do you mean?
Well, this is that paper that's probably referenced there, that Dr. Maria, she separated, she had a pre-existing paper that had long, medium, and short eyes, axial lengths.
Oh.
And then she divided into images. I was just trying to keep track of what I was looking at. It's kind of
because the anterior chamber is very...
Yeah, you can see that something short. That's a very short ACD, isn't it? So, which might be a related thing. You know, it could be that if you've got a very short ACD, maybe you need this blocking or transmission or something. I don't know.
Last question.
Thank you. This is a very nice work, of course. I wanted to add a comment here about the appearance of those images in the far periphery. You know that we've been capturing similar images in vitro in a physical model eye. Our experience is that, first of all, the double image exists in many angles before the shadow, and the shadow appears at the angle for which the light through the IOL is apodized completely. So this is where you get the local medium, which appears like a shadow. And the other thing is that in these wide angles, there is so much astigmatism that the appearance of the image depends a lot on peripheral refraction. So it depends a lot how we adjust the focus of the camera. With a little bit of change in this, you can make even this photopsia disappear because of the blur in the horizontal direction, in the field direction.
We should probably summarize it all and see what it is. Just like in some of those papers, like even the blind spot was reported as being a shadow. You know, it's like you're not paying attention. You can see shadow like it is.
Okay, thank you very much. Now
everyone, I'm here today to do a presentation on comparative study of IOL corrections in keratoconic eyes with and without RGB contact lenses. Before starting the study, we will just go through some of the basics, a bit of background. Now, most of you might know what this is. It's an eye affected by cataract. And when an eye is affected by cataract, the crystalline lens loses some of its transparency and the lens needs to be replaced by an artificial lens or intraocular lens IOL. Now, this process, there's a biometric scan, manual calculation, when IOL is chosen. Now, what if a patient who needs an IOL surgery also has another condition called keratoconus? Now, keratoconus is a condition where the cornea of the lens progressively gets protruded, and as a result, because of which the corneal curvature, as you can see in the figure, when there's a protrusion, and as a result of it, there will be a lot of aberrations in the eye, like coma, astigmatic, and several higher aberrations. This really complicates the situation, especially when it comes to an IOL corrections. So in keratoconus, in order to correct keratoconus, there's like spectacle correction if it's in the early stage, if it's mid stage, there's like rigid gas permeable contact lenses, and because of the astigmatism in the keratoconic eyes, most of these corrections are with toric corrections. And when it comes to an IOL correction, there also is a assumption that toric IOLs can be corrected. Toric IOLs can be used to correct the keratoconic eyes. There are a lot of publications where the same as said that toric IOL can be used to correct a keratoconic eye. So here, in this comparative study, we like to compare different situations and see whether toric IOL is a most suitable IOL correction for a keratoconic eye. And here we are, this whole study here is done in a virtual medium, in a virtual place, and different correction strategies of IOL corrections are going to be tried out and see. Because in real life case, as always a surgery, there's only one chance, right? One correction. But here, since it's a virtual case, different corrections, different IOL corrections and contact lens corrections combined with IOL corrections are tested out in keratoconic eyes, and we can see which is the best case scenario. So for methodology, first we need a set of eyes where the study needs to be done, and these eyes are generated by SIND eyes, a statistical eye model which gives a very realistic biometrics of normal and keratoconic eyes, using which the eye is optically simulated, and then the eyes are retraced through a MATLAB retracing program where the whole where a parallel beam of light of 555 nanometer, 3 mm diameter light is retraced to the eye, and the resulting wavefront is analyzed. And to see what is the image quality of the wavefront, what is the visual acuity of wavefront, an image metric called visual stress ratio is used to determine the visual acuity of the eye. And now a different kind of lenses would be used, contact lenses, IOLs, different kind of lenses would be used, and to see which would be the, to get the power of each lens, a scanning algorithm is used. So we know in terms of IOL corrections, IOL power equations are used to find power, but here instead we are using a scanning algorithm that scans to the spherocylindrical space through multiple steps until the resulting lens could give a maximum of PSX. The same algorithm is used to find the light correction, whether it's a contact lens or IOL used. So there will be an IOL and contact lens correction used, and for contact lenses, it will be rigid gas permeable contact lenses, and for IOLs, bag in the lens intraocular lenses are used. So bag in the lens IOLs is a bit different from traditional IOLs. You can see from the figure where there's like two haptics, so perpendicular here, and you can see a wedge between here. This is implanted also a bit differently, where two capsular openings are made in the eye, both in the anterior and posterior capsule, and the IOL is wedged between the capsules in the lens equator, and that's how the IOLs are implanted on the eye. So with the methodology, now let's see what are the cases that will be analyzed in the study. First, we need to know the initial state of the eye, the uncorrected state. Please note all the eyes in the study, there are 20 keratoconic eyes. None of the eyes have cataract, or the effect of cataract was not simulated for the eyes. And these eyes show a moderate to severe case of keratoconus. And after analyzing the initial case of the eye, then the eye is then corrected by a contact lens correction, RGB contact lens correction, and then an IOL correction, both spherical and toric IOL corrections, and then a combination of IOL and a contact lens study. So we can do an example of how it's done. So first we'll say we can do the uncorrected case. This is SIND eye 15, and you can see the retracing of the whole eye and how the corneal map of the eye, and how the light rays are behaving at the retinal plane and resulting wavefront and the VSX as a result. And then the eye is corrected using a contact lens correction, and then afterwards the lens is removed and an IOL is placed, then a spherical IOL correction, and then the spherical IOL will be further corrected by a spherical contact lens, then a spherical IOL correction plus toric IOL contact lens. Same would be repeated for toric IOL as well, toric IOL plus spherical contact lens, toric IOL plus toric contact lens. This is how it's done for 20 keratoconic eyes, and this is where the results look like. So this is the lowest case of VSX is when the eye is uncorrected, no surprises there, and the highest VSX is when the eye is corrected by a contact lens correction. That's all fine, but then let's look at the IOL corrections. When it comes to IOL corrections, when it's just the IOL, the keratoconic eye is just corrected by the IOL. Toric IOLs give a significantly better VSX little bit better VSX compared to the toric IOL gives a little bit better VSX compared to the spherical IOLs when it's just IOL corrections, and then when both the contact lens and IOL corrections are implemented in an increasing order of VSX, that will be toric IOL plus spherical contact lens, spherical IOL with spherical contact lens, toric IOL with toric contact lens, and the spherical IOL with toric contact lens. So among the IOL corrections, the highest VSX is given by spherical IOL with toric contact lens, and toric IOL and toric contact lens correction gives significantly lower VSX. This is mainly because when it comes to toric IOL, what toric IOL is most suitable to correct is regular astigmatism, which most certainly is not the case with when it comes to keratoconic eye, which has a very irregular astigmatism. But still, the toric IOL can try to correct some part of the aberration. But later on, this will be the case with a lot of keratoconic eyes that even after eye implantation, they might need a contact lens correction. And when they are corrected by toric contact lens, this tend to be a little bit of an overcorrection, because how our RGB contact lens works is there's the lens and there's a cornea, and in between them there's a tear film that does an index matching, and this lets the eye to be rid of like 60% of the aberration. So whatever the eye will corrected, by the time the contact lens is placed, those aberrations are not like really there. That's the reason when it comes to toric IOL and toric contact lenses, a slightly lower VSX can be seen in the comparison between the wavefronts. So altogether, the contact lens plus IOL corrections give a better VSX compared to the IOL corrections, again mainly because of our RGB contact lenses apt with the keratoconic eyes. So at least when it comes to moderate to severe cases of keratoconic eyes, contact lens correction might be required for a better result, and this makes one wonder whether whatever be the IOL correction, the eye would at the end of the day might need a contact lens correction. So whether the IOL power really matters or not, but it's not the case the IOL power really matters, because contact lenses are not permanent, so the patient would still there be cases where the patient would not be using a contact lens, and they should still be able to have a decent vision, because of which finding the right IOL power is important. But it's good to be taken into account that at the end of the day, the eye would still need the keratoconic eye might still need a contact lens correction on top of it. So on concluding, among all the IOL corrections, according to this study, spherical IOL with a toric RGB lens provides the highest image quality, and IOL corrections alone cannot adequately compensate for the several of the corneal aberrations in the keratoconic eye, at least compared with the contact lenses. And toric IOLs, although individually, when it's just the toric IOLs, it's slightly better than spherical IOLs. But when compared to contact lens corrections, toric IOL seems to underperform. Thank you.
Questions?
So, Sharon, nice to see you in person. What pupil size did you choose?
5mm.
Oh, thank you.
Go ahead.
So this is some simulation. If you can go back to slide number 10 with your results, I'm just wondering which parameters that you enter to generate those keratoconic eyes contribute mostly to this increasing variation in standard deviation.
The parameter that will be considered, the VSX is calculated from the wavefront, the resulting wavefront from the eye. That's how the VSX was calculated.
Okay, but have you checked why you're getting higher standard deviations with those corrections? Because as you, like we can see that they are increasing.
Standard deviation, the error bars you mean? Yeah.
They are related to error bars.
Yeah, the error bars in some cases, yeah, you could see because it's very eyes, and I think it's in some cases
No,
it's a bit.
but you are simulating this, right? So you can actually investigate, right, why this is happening and which parameters contribute to this large standard deviation. Yeah?
Okay, yeah.
That's a suggestion.
Look into it, yeah. Thank you.
Yeah.
Yes, thank you for a nice talk. I would like to ask you about, it's not clear to me why the contact lenses by itself would be the best option.
Contact lenses by itself, because I said like it's RGB contact lenses, GPS permeable contact lenses, and when it is put on the keratoconic cornea, which has a distorted shape, when there's a, between the lens and the cornea there's a
yeah, it's correct in aberration. Yes, but I was wondering why does it perform better when you don't have the IOL there? That's what you said, because that's what you're showing.
Well, with the IOL, it's a monofocal IOL, and what I felt like when I was doing all these operations with an IOL, there's a little bit of spherical aberration and all coming, because and even with the toric IOL, there's some aberrations that are there, which was not there when there's just the slide there. So one thing with the IOL, at least the monofocal IOL, it happens.
That was actually my question. Sorry. I had the same question. So when you introduce the spherical IOL, you are introducing extra spherical aberration. That's that is not corrected by the contact lens. So if you would redesign the contact lens to compensate for the spherical aberration introduced by the intraocular lens, you would have the same result. So
but we designed the contact lens, maybe it works, but it's just that if I make necessary changes in the IOL, according to the contact lenses, it's just that when the contact lens is off, the difference could be a bit more staggering.
You could change the anterior surface of the contact lens to compensate for part of the spherical aberration introduced by the intraocular lens. So that's why you have that difference in result, because you have a mismatch in spherical aberration. That's
Thank you.